तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In this lecture, we will continue our discussion of the analysis of two-port networks using the various network functions that we have defined so far. Often we have a situation where a two-port network is terminated in a load which has, let us say, as an impedance function ZL of S or an admittance function YL of S. We would like to find out the ratio of the voltage V2 to V1 under these conditions, the input impedance measured under these conditions, and so on and so forth. So, analysis of such networks can be done on the basis of the Y parameters or Z parameters or other sets of parameters. Let us take the Y parameters to illustrate. So, I1 equals Y11 V1 plus Y12 V2, that is a standard equation. I2 equals Y21 V1 plus Y22 V2, standard equation. But now, because of the load termination, V2 and I2 are constrained by this load impedance. In particular, we have I2 equals minus YL times V2, because YL times V2 is the current in this direction, but since our reference direction for current is opposite, therefore I2 will have to be written as minus Y2 minus YL times V2. This is the restriction. Therefore, here we have written I2 equals Y21 V1 plus Y22 V2 equals minus YL times V2. From this, we can eliminate I2. Therefore, you take this equation V2, when transfer this on the other side, minus of Y22 plus YL times V2 equals Y21 V1. This gives this relation V2 equals minus Y21 divided by Y22 plus YL V1. So, when you substitute this into this, you get a relation between I1 and V1. So, for V2 you substitute this equation, then you get a relation between I1 and V1. Therefore, the input admittance at port 1, when port 2 is terminated in a load admittance YL, can be obtained as I1 over V1 with load at port 2. This can be written as Y11 minus Y12 Y21 over Y22 plus YL. It can be shown like this. Similarly, the input impedance, which is of course the reciprocal of that, but you can independently write this as, you can show this Z11 minus Z12 Z21 over Z22 plus ZL. Alternately, this can be written in terms of H parameters, H11 minus H12 H21 over H22 plus YL. In terms of the ABCD parameters, you can write this as AZL plus B over CZL. So, these are in terms of the various network parameters, we can find out the input impedance or admittance in this form. The derivation of this, I will leave this as an exercise for you. Similarly, the voltage ratio G21 of S, which is V2 of S over V1 of S with load termination, is also important, because in any filter problems and so on, you terminate this two port in a load and you would like to find out the ratio of V2 of S to V1 of S. Analyzing in the same fashion, you can show that this is equal to Z21 ZL divided by delta Z, the determinant of the open circuit impedance matrix, times Z11 ZL, can also be shown to be minus y21 over y22 plus yl. You can also show this to be equal to minus h21 over delta h plus h11 yl. These are all straightforward relations which can be obtained by simple manipulation of these various equations. ZL equals ZL in terms of the ABCD parameters A ZL plus P. A ZL plus P. So, in terms of the various network functions, you can calculate the network functions that are of interest to us in a terminated condition. Note that we have used the capital G here to distinguish between small g. When under open circuit conditions, the ratio of V2 V1 we use small g. In general load conditions, load terminated conditions, we use the capital G. Similarly, instead of small y11, we can write capital Y and Z in this case, because they are not under normalized terminal conditions, but under specific loads which are defined by ZL or YL as the case may be. It is often convenient for us to analyze a complicated two-port network as the interconnection of simpler two-port networks. For example, I may have a complicated two-port network which can be thought of as the interconnection of two-port networks A and B. Or put it another way, let us say there is a two-port network A which is connected to a two-port network B in this fashion. Now, this is called a parallel interconnection because port 1 of the network A and port 1 of network B are connected in parallel. The same voltage V1 appears across port 1 of A and port 1 of B. The same voltage V2 appears across port 1 of A and port 1 of B. So, this is called a parallel interconnection. Both ports are connected in parallel, and now it would be possible for us to find out the Y matrix of the overall configuration in terms of the Y matrix of the A network and the Y matrix of the B network, provided some conditions are satisfied. Suppose we are having only port A, network A in operation. It is not connected in parallel with network B. That means you disconnect this. Then port requirement gives us the condition that I1A must be equal to X. That means the same current must flow to both the terminals. The port requirement is I1A is equal to X. That would be true if network A was operating in isolation. Similarly, I2A is equal to P. On the other hand, if port B alone was operating, I1B equals Y and I2B equals Q. Now, when you interconnect them, when you put them in parallel, then if the same conditions are still valid, that is X continues to be equal to Y1A, P continues to be I2A, Y continues to be equal to Y1B, and Q continues to be Y2B after parallel interconnection, then port conditions are not violated. Then it can be shown that the Y matrices of these two will add up to form the overall Y matrix of this network. The proof will be something like this. If the total current is I1 and this current is I2, then we can say that I1, I2, these two currents are equal to I1A, I2A plus I1P plus I2B, because as you can see, this current I1 is I1A plus I1B, I2 equals I2A plus I2B. This is how it will be. And now this will be equal to the Y matrix of the A network times V1 V2 plus the Y matrix of the B network times V1 V2. And you can now have this the common matrix, therefore you can write this as YA plus YB multiplying V1 V2. That means the overall Y matrix of this two-port network is YA plus YB, where each of these is a two-port matrix. That means when you have two two-port networks in parallel, Y equals YA plus YB. as long as the port condition is not violated. And you can take it for granted that as long as we have 3 terminal 2 port networks, that means this is a common lead going through. When you have a 3 terminal 2 port networks, the port condition is never violated and this particular rule will be always valid. In other cases, we have to take special tests, you must make special tests to see that the port conditions are not violated. As an example, suppose we had this same example which we considered earlier, where we had this 2 port network of 1 ohm, 1 ohm, 1 ohm and 1 farad. You can consider this to be the parallel connection of one 2 port network containing 1 farad capacitor, the other 2 port network containing 3 star connected resistances. So, you have the parallel combination of these 2 networks A and B. And if this is 1 ohm resistances, this can be converted into 3 a bit pi connected set of 3 ohms resistance as we have seen, and it turns out that the A matrix, the Y matrix for the A network for 1 farad capacitor turns out to be S minus S minus S S. The Y matrix for the B network turns out to be 2/3 minus 1/3 minus 1/3 and 2/3. So, for this entire network, the Y matrix is the sum of these two. This will be the Y matrix for this will be S plus 2/3 minus S minus 1/3 minus S minus 1/3 and S plus 2/3. This is the result which we have already obtained. So, it turns out that when 2 networks are coming in parallel, as long as the port conditions are not violated, the Y matrices add. Similarly, it can be shown that when 2 networks are in series connection, this is said to be series connection, then again when the port conditions are not violated, that means this current continues to be the same as this current, continues to be the same as this current and continues to be the same as this current. The port voltage V1 is V1A1 plus V1B, the Z matrices add ZA plus ZB. However, the port conditions are violated in this case for most of the practically useful networks, and therefore, this particular interconnection is not very much used. It can be similarly shown that in the case of H matrices, it is you have one set of ports are connected in series, another set of ports connected in parallel. I will leave this as an exercise for you to figure out what type of interconnection is called for if we have to have the sum of the 2 H matrices as the component networks to be added together to give the H matrix as the resultant network. However, for the ABCD matrices, the interconnection is what is called a cascade interconnection. That is what we will discuss in some detail, because that is practically important, and there we will have the overall port configuration, overall port chain matrix or ABCD matrix is obtained as a simple product of the ABCD matrices of the individual networks. We will see that in a moment. I will not discuss the series connection or the series parallel connection pertaining to Z and H matrices, because it is not ordinarily very important and useful in practical work. Two port networks are said to be connected in cascade when they are connected in this fashion. That means the input quantities to 2 port network A will be there, and then the output quantities of network A turn out to be the input quantities for network B. That means, if you use this as a transmission line, the receiving end quantities of network A will turn out to be sending end quantities for the network B, and this will be the output of this. So, we see for as far as network A is concerned, if TA is the transmission matrix or the ABCD matrix, V1A I1A as far as A is concerned is related to V2A and minus I2A with this difference direction by this chain matrix or the transmission matrix TA. So, V1A I1A is the ABCD matrix pertaining to network A, which I had indicated as TA, multiplying V2A minus I2A. But we observe that V2A is the same as V1B. The port voltage of second port voltage of A turns out to be the first port voltage of B. So V2A is the same as V1B, and minus I2A is the same as I1B, the input current to port B of the network at port 1 of network B. So minus I2A equals I1B. Now what is the usefulness of this representation? You observe that V1B and I1B are related to V2B to minus I2B by the chain matrix of network B. So V1B I1B is obtained as TB times V2B minus I2B. So if you substitute for V1B I1B TB times V2B minus I2B, it will be TA times TB times V1B minus I2B. That means the input quantities here will be related to the output quantities in the overall 2-port network. Suppose you consider this as an overall, the cascade as an overall 2-port, then that the relation between the input quantities and the output quantities is the product of the two chain matrices TA and TB. So you have V1A I1A as the chain matrix of this turns out to be TA TB multiplied by this. So in the cascade connection, if two 2-port networks are connected in cascade, the chain matrix or the cascaded network is the product of the chain matrices and the individual links in that chain. That is why this is called a chain matrix. So you can see that if I have a whole lot of these networks in cascade, so suppose A, B, C, D in cascade, all the 4 2-port networks put in cascade, the overall chain matrix of this is TA times TB times TC plus TD, where these are all individual matrices. The product of all those matrices will give us the chain matrix for the overall configuration. This is a very convenient arrangement. Now in doing this, in calculating the chain matrix of the overall configuration, it is important to see that for simple networks like this, suppose I have this as a 2-port and this as Y, the chain matrix, as we have seen in an example which worked out earlier, you can go back and see the chain matrix for this is equal to this. Very simple. Suppose you have a shunt element, the chain matrix of that is 1 1 0 Y. On the other hand, if I have a series impedance Z like this, the chain matrix for this is 1 Z 0 1. So if you remember these two relations, the chain matrices were very simple networks. When you have a cascade connection of a whole lot of these elements, it's very easy to figure out what the chain matrix of that would be. An example will illustrate this. Suppose I have a network like this. This is what is called a ladder network. This can be thought of as the cascade connection of this 2-port network, another 2-port network, a third 2-port network, a fourth 2-port network, a 5th one, and a 6th one. So we have 6 2-port networks, very simple configurations like this, all put in cascade, giving us the overall configuration. Let us take some numerical values. 1 ohm, 2 Siemens, 3 ohms, 4 Siemens, that is the conductance, 5 ohms and 6 farads. So to obtain the chain matrix of the overall configuration, I need to multiply the chain matrices of the individual units. Remembering this rule, the chain matrix for the first 2-port network is this, that is the one. For the second 2-port network, it is 1 0 2 1 using this rule, because it is a shunt element. Similarly, for the third 2-port network is 1 3 0 1. For the fourth it is 1 0 4 1 because it is shunt element. Fifth again a series element 1 5 0 1, and the last is again a shunt element 1 1. The admittance of this element is 6s in terms of the generalized admittance functions. So that is your overall chain matrix. So you can write this down by mere inspection, the chain matrix, the ABCD matrix of the overall configuration, and if you multiply this out and simplify, this turns out to be 1350s plus 43, that is the A parameter, B parameter is 225, C parameter is 942s plus 30, and 157 is the D parameter. So that is the ABCD matrix of this overall configuration. We have seen that you can verify that this follows the reciprocity condition AD minus BC equals 1, and you can see that the chain parameter or the ABCD parameter of a cascade of a overall network can be thought of, particularly in this form which is called a ladder network, can be thought of as the cascade connection of simple networks. The chain parameters of each of these is written down by mere inspection, and it is a question of algebra to find out the overall chain matrix. Let me now summarize our discussions on the topic network functions. We started with the general definition of a network function as the ratio of Laplace transforms of the response, which is a current or voltage, to an excitation, which is again a current or voltage. So this is a general network function, and we said that for a passive network, the poles of this network function represent the natural frequencies under appropriate terminating conditions, appropriate conditions, and the restrictions on the poles of the network function will be such that all the poles must be in the left half plane. They can be marginal in the imaginary axis provided they are simple. This is from the point of view of stability, which is a requirement for a passive linear network. And when you talk about the network function, it is the ratio of Laplace transforms, it is not the ratio of time functions. This is what you should keep in mind. Then we went to study the network functions appropriate to one port and two port networks. For one port networks, the ratio of the excitation, which is a voltage, to the current, or vice versa, are the two network functions that one can define. This is the driving point impedance function or the driving point admittance function, which are reciprocals of each other. We observed that the reciprocal of a driving point function is also a network function, and therefore both the poles and zeros of driving point functions have got to satisfy the requirements of their locations, restricted locations from the point of view of stability. Then we discussed the various sets of parameters characterizing a two port network. We defined the Z parameters, the Y parameters, the hybrid H parameters, the inverse H parameters are called the G parameters, the ABCD parameters. Of these, the Z parameters represent are pertain to essentially to a network with the two ports open circuited, because you introduce current excitation. When the current is removed, the particular port is open circuited. That is why they are called open circuit impedance parameters. Similarly, the Y parameters are appropriate to the network with the two ports short circuited. They are called short circuit admittance parameters. The H parameters refer to networks when both one port is open, the other port is shorted. Therefore, they are called hybrid parameters. As far the ABCD parameters are concerned, there is no particular designation of open circuit or short circuit associated with that. In fact, we saw that the ABCD functions as a S are not respectable network functions because they are not in the ratio of the Laplace transform response to excitation. As a matter of fact, the inverse of ABCD, the reciprocals of these are network functions, which we have seen. Therefore, the poles of ABCD do not represent the natural frequencies. It is the reciprocals which represent the natural frequencies of the network under appropriate conditions. We worked out various examples to calculate the network parameters or the ABCD or the various parameters of a two port networks. Then we also saw how a loaded two port network, that is a network terminated in a particular load impedance, can be analyzed using any one of the sets of parameters. In particular, we found the input impedance of a 2-port network terminated in a load impedance ZL, we also saw the voltage ratio V2 to V1, how it can be calculated in terms of the various parameters Z, Y, H or A, B, C, D. We observed that a reciprocal 2-port network has got certain definite restrictions on the parameters. So, out of the 4 parameters in each set, only 3 are independent. Reciprocity requires that Z21 equals Z12, Y12 equals Y21, H12 is equal to minus H21 and AD minus BC is equal to 1. Similarly, the requirements of symmetry were also discussed, and then we also finally saw that how a complicated 2-port network can be viewed as interconnection of subnetworks, sub 2-port networks, and of these various interconnections that are possible, the parallel interconnection is appropriate to the Y parameters. As long as the port condition is not violated, the Y matrix of the overall 2-port is the sum of the Y parameters of the individual 2 ports. Similarly, in a cascaded system of 2 ports, the chain parameter, the chain matrix of the overall 2-port is the product of the chain matrices of the individual 2 ports, but you must keep that order intact. For example, if you have got here T equals TA, TB, TC, CD, you must maintain that order in that cascade chain. So, that is the rule with reference to the chain parameters. Similarly, as far as Z parameters is concerned, the series connection will mean that the overall Z matrix, the sum of the individual Z matrices provided the port conditions are not violated. Similarly, the H matrices will add when one port is in parallel, the other pair of ports is in a series, and the interconnections relating to H parameters, there is series parallel interconnection or the series interconnection are not very common, not very useful in practice. So, we did not discuss them at length. So, at this stage I will give you a set of examples for you as an exercise to work to illustrate the ideas that we have discussed under the heading network functions. First problem in this exercise deals with a 1-port network. This is a linear 1-port network with an admittance function Y of S. The driving point admittance is Y of S, and it is given that Y of S has poles at S equals -1 plus or minus J1. Poles at S is equal to -1 plus or minus J1 and 2 zeros. The locations of the zeros are not known to us. So, this is a network function with a quadratic in the numerator and a quadratic in the denominator with a particular scaling factor. The zeros are not known, the poles are known to be at -1 plus or minus J1, the 2 complex conjugate poles. Further data given to this network is the current under steady state conditions for different types of excitation voltages V. So, if V equals 6 volts DC, if the applied voltage is 6 volts DC, then the steady state current into the network is 0. It is known that this is 0. Now, a second excitation is when the input voltage is sin t volts, if you drive this network, 1-port network with a sinusoidal voltage source sin t, the steady state current is 0.6 sin t plus 0.8 cos t amperes. So, when you drive this 1-port network with a sinusoidal input voltage sin t, this happens to be the current. You are asked to find out the current when the input is sin 2t volts. If the input is sin 2t volts, what is the steady state current for this network? So, using these 2 items of data, you should be able to calculate the locations of the 2 zeros as well as the scaling function that we are having, because after all the network function of this will be of the form H times Z1 is S minus Z1 times S minus Z2 divided by S minus P1 times S minus P2, but P1 and P2 are known. So, 3 constants are to be evaluated using these 2 items of data. Using that, you must be able to find out the steady state current when the input is sin 2t volts. Second example. You have a 2-port network of this configuration. 1 ohm, 1 farad, 1 farad, 2 henries, 1 ohm. You have the input voltage V1. So, first question is find the transfer function V2 of S over V1 of S for this network. So, the Laplace transform of the output voltage V2 of S, V2t to the Laplace transform of the input voltage V1. Then B, determine V2 of t if the input voltage V1 of t is a unit step function ut assuming 0 initial conditions. So, assume that all capacitors are initially uncharged and the inductor does not carry any current. Using this transfer function, given this particular input excitation, find out the output in time domain. C, sketch the magnitude of the frequency response function this V2 of S by V1 of S, I will call that G21 of S. So, response function G21 j omega as a function of omega, magnitude of the frequency response function as a function of omega. That is, in other words, you have to plot G21 j omega magnitude as a function of omega, whatever curve you get. Problem number 3, you have given a 2-port network here, find the Z, comma, Y, H and ABCD parameters of the 2-port networks A and B. There are two 2-port networks. For each one of these, you find the Z, Y, H and ABCD parameters. First network consists of 1 ohm resistance, 1 Henry inductance, 1 farad capacitor, 1 ohm resistance, a ladder network. Second 2-port network, 1 ohm resistance, 2 ohm resistance, 2 ohm resistance and a dependent current source here, whose value depends upon the input current I1. So, whatever current I1 have here, the current here is 3 times I1. So, this is a dependent current controlled current source, and therefore, you will find that this network is not going to be reciprocal. This is a reciprocal network, this is not a reciprocal network. So, you will expect that Z12 is not equal to Z21, Y12 is not equal to Y12, H12 is not equal to minus of H21, and the determinant of ABCD parameter matrix is not going to be equal to 1 for this network B. Fourth problem, find a suitable two-port network satisfying each of the following matrix specifications. So, this is the reverse of analysis you are given the matrix specifications, you have to find a network which satisfies this. You can use the concept of equivalent networks to do this. A, the Z matrix of this 2-port network has to satisfy these relations. Is the Z matrix of this. B, the Z matrix of another network 4, 2, 3, 4. So immediately you see that this is a reciprocal network, this is not a reciprocal network. So you need to incorporate some dependent sources in order to find a network which has got this Z matrix. C, the Y matrix for this is 5, minus 3, minus 3, 6. D, Y matrix for this is 5, minus 3, let us make it plus 3, this is minus 3, again 6, again this violates the condition for reciprocity, therefore the network that you get here cannot be modeled using purely bilateral and reciprocal elements. E, the T matrix, the ABCD matrix for this is 26, 5, 5, 1. You observe that the determinant of this T matrix is equal to 1, 26 minus 25 equals 1. So it should be possible for you to find out a reciprocal network satisfying this. F, the H matrix for this is 4, 2, 1, 4. So you find out for each one of these specifications a simple 2-port network satisfying the specifications. Problem 5 concerns what is called a doubly terminated 2-port network. This network N, 2-port network 1, 1 prime, 2, 2 prime is terminated in load resistance RL at one side and you have resistance R0 in the other side. So in that you introduce a voltage source VIFS. So there is a you can view this as a termination of N, or you can view this as internal resistance of this source, whatever it is. So we have a resistance at one side and a resistance on the other side. You are asked to find the transfer function V0 of S over VIFS of the terminated two-port network N in terms of, naturally you must have R0 and RL entering the picture, R0, RL and the Z parameters of N. We have done a similar example in the lecture where there is only RL, R0 is 0. Now we extend that to find out the ratio of V0 of S to Vi of S in terms of the Z parameters and R0 and RL. This is a very practically important situation where N could be a filter network where you have a source with an internal resistance R0 and the filter is terminated in a load resistance RL. This is a very practical situation and you try to find out V0 of S over Vi of S in terms of R0 and RL and Z parameters of the network N. 6. Next problem is slightly complicated network. You have these boxes represent resistances. So you have two T networks, these three elements constitute a T, these three elements constitute a T and two T networks are put in parallel. This is 2 ohms, this is also 2 ohms, this has a 2 farad capacitor, 1/4 ohm resistor, 4 farad capacitor and 4 farad capacitor. So, this is the overall 2 port. So, the question is find the y parameters of the overall 2 port viewing it as the parallel combination to two-port networks. So, it means yes that you have to consider the T network constituted by these 3 elements as one 2-port network, the T network constituted by these 3 elements as another 2-port network. Both of them are now in parallel. Find out the y parameters of network A, find the y parameters of network B, add them up, that will be the y parameters of the overall network. Seven. So, this is a 2-port network which is built entirely of resistors. This has the ladder configuration. Find the ABCD matrix of the 2-port network viewing it as a cascade connection of simpler networks. So, think of this as the cascade connection of several simple 2-port networks. Find out the ABCD matrix of each one of these simple networks, multiply them up and you get the overall ABCD matrix of the entire configuration. Last example, we have a 2-port network N terminated in a load impedance ZL of S. Let the open circuit impedance matrix, that is the Z matrix of N be 0 minus R 0. That means the Z matrix of this is Z11 and Z22 is 0, Z12 is minus R, Z21 is equal to R. This is the situation for this. Now, if you measure the input impedance here ZIN of S with this load termination, find Z input of S, that is the input seen at port 1 when the port 2 is terminated in ZL of S in terms of this R which forms a component in this matrix and ZL of S. If ZL of S is the impedance, suppose ZL of S is taken to be one capacitor, suppose that means 1 over Cs. Show that the network behaves like an inductor at the input terminals. That is, if this terminating impedance is a capacitor, as you see from the input terminals 1 1 prime, it behaves like an inductor. So, this is the property of a network which has got this kind of 2-port open circuit impedance matrix, and as I mentioned earlier, this is characteristic of what a device called gyrator, which I mentioned in passing while discussing the theory. And so, a gyrator terminated in a capacitor is equivalent to an inductor at the input terminals. So, you work this out, find out Z input in terms of a general ZLFS, and if ZLFS happens to be 1 over Cs, find out the corresponding input impedance in terms of R and C.